Come on in, everyone. I'm waiting for a few more people to get in before I start making announcements. So don't fret it that I'm not starting yet. I know class time has started, but not too rushed. Well, we got 8 of you. We had 20 something last time. Are you any of you in the lab where Megan was, or with Megan, the girl that asked me a question in the class? Just because she never emailed me, and hence I haven't been able to give her the invitation to the Zoom course, and I just was trying to get it to her. I don't see her up here either. I don't think she's logged in. Maybe she got it from somebody else and she's good to go. I'm not sure. Another one here. All right, class is supposed to start, but we still only have 8 of you, nope, 9 of you, 10 of you. Oh, Megan's made it. Good deal. So they answered the last question. And try to see if my iPad can work to make sure it can link up, All right, got a few more people coming in. Zero 1 0 8 2 0 2 4. Some more people coming in. It looks like everything's working there. And we have a pretty good fraction of the class here. It looks like we now got 16, 15 people in here. So I guess we'll go ahead. So those of you who met with me this morning, hopefully that's all of you guys. There may be some of you that are not taking my lab or not wanting to take my lab. And like I said, we can work that out. It's more of a matter of making sure the other lab instructor approves it, because I'll approve it and that lab instructor might approve it as well. So you just got to make sure you contact them and see if that's possible. The only thing that would make them, usually in my experience, the only thing that would make them not accepted is if they just have too many people. Our labs are sort of set up to fit exactly 24 students. We could make, room for maybe 25 or 26. It gets a little more complicated after that. So anyways, make sure you contact Ms. Raskovich and let her know if that's what you're wanting to do. Otherwise, just stick in my lab, and you can do this later on too. It might be something where you just have to do for first couple of weeks, and then you'll have a few people dropped, and she might be cooler with you switching at that time. So let me know. If you go into Canvas now, you'll notice that I've already made some pretty significant changes. For instance, in our Canvas course, we now have a bigger version of week 1. We also have the interesting science-related links and documents, helpful documents and links. The syllabus isn't in there, but that's where it will be. Chapter practice, practice tests, and online tests. Actually, the chapter practice is published, but the practice tests and online tests are not published yet. That's why you can't see them. Same thing with the face-to-face tests. You can't see those either. But week 1 now has several videos from my YouTube channel, as well as some documents for labs, significant digit rules, sig figs when they fail, videos, all sorts of good stuff. So hopefully you can find quite a good amount of material there that will help you in case you're misunderstanding something. Let me look. I'm going to check. If you click on chapter 1 homework in week 1, that should now take you to the MyLab and Mastering page. And it should also give you the option to enter your access number, your access key or your pass key, or to pay for it, that sort of thing. So make sure you check out all that. I don't know why, but it automatically lists the dates on here, but I got that fixed. So chapter 1 homework's available, as well as chapter 1 part 1 homework is available. Anybody have any questions on anything so far? Still got people coming in. Wow, really late. So chapter 1, let's look and see what it is. Yes, so chapter 1 homework and chapter 1 conceptual are both posted and have the appropriate dates on them, at least on the mastering side. So make sure you go ahead and do that. You don't have to do anything once you do a homework in mastering. It automatically propagates to my Canvas page and actually enters into my Canvas gradebook too by itself. If, however, at some time you see that the grade in my Canvas gradebook is different from the grade you have in my lab and mastering, what you want to do is wait till at least after midnight, the day that you see it, and see if it changes the next day. If it doesn't, then you need to let me know, and we might have to fix it. Be advised, I do correct all that by the end of the semester too. So even if I don't get around to it, I'll definitely find the error by the end of the semester. All right. So this chapter 1, is called Introduction, Measurement, Estimating. So basically, we're talking about how science works. I do a slightly different discussion of how science works. I treat science like a cyclic process. Specifically, you can imagine, for instance, you observe some thing occurring, and I've often used examples like you see a kid throw a ball, and then maybe it's like a toddler, so they're kind of not that skilled, certainly not quote unquote athletic necessarily as a small toddler, but you might see them like with their arm completely straight just throw a ball like that, like they're, I don't know, I like to say morons, but it's just because I find it entertaining to pick on kids that are not actually seeing the picking on, but just acting like I'm a jerk that don't like kids, which is really the opposite of reality. I love children in general. So if you did see a kid throw a ball, you'd see that the ball would leave their hand and it makes some kind of trajectory and land on the ground. And this is going to sound really far-fetched, but to be honest with you, this is one of the ways that science does work. You could model that on something as simple as, I believe the ball, when released from a person's hand throwing, will follow the path of a circle. And the circle will have a radius that's equal to the distance from, let's say, the bottom of the person's feet to the bottom of the ball when it's released from their hand. That distance would then make the circle go like this. And then you could go back and follow up and look at it and see if it really does match that. And as you got further and further along, you'd find that there is a slight deviation between that shape that the ball makes and the circular shape that a ball would make. And you might try to address that by saying, well, maybe I missed the right radius. Maybe the radius is from, their ankle to the bottom of the ball. Or you might say, well, maybe the shape isn't a circle, it's something different than a circle. So you try some other shapes that you know the geometry for. All that sounds kind of stupid, really. I mean, you're basically just taking a geometric shape and assuming it's having it with no real physical reason behind it. But to be honest with you, that's a lot of how sometimes science is fixed. So what you would do is you would make that observation, and from that, you would basically make a model, which is in some sense a hypothesis. And then that hypothesis being more robust as a model, versus giving it the very specific data of a circle being the shape and the radius being the distance from A to B and all that, that allows you to then make a prediction. So you can say, well, I predict that the next ball thrown will land this far away if the person's this height, and so on and so forth. So then you go back to the observation process and try it again. And that's sort of what science is. It really is something where you can make an observation, you make a hypothesis, and then you make a prediction. So let me see if I can actually share my screen from my iPad. Now, this was working, so hopefully it will continue to work, but we always have some issues with that. Let's see. So there we go with that. So I'm pulling up my iPad. Now, the key part about this cyclic idea is if you include astronomy as a science, it makes a little better sense because I use the word observation. So what I'm going to put up here is observe. Because in astronomy, we can't, literally make a star. We can't make a planet. We can't make a star system. We can't make a galaxy. So we're sort of left with observing what exists in nature. So in that sense, you can see that an observation is sort of the same thing as experiment, but obviously I would sometimes like to write observe/experiment. And then from that, you make a hypothesis. And then from that hypothesis, you can make a prediction. Now, this will be slightly different than what your book does, but it's in the same spirit. But to be honest with you, when you start taking the practice tests and the regular tests, you really need to lean more on what the book is saying, because I'm literally will take on practice tests and tests. I'm literally taking some of the test bank material straight from the author. So it's really wholly produced based on Gene Coley's writing. But this is the way I see science as, and the scientific method is progressing. So you make an observation. From that observation, you make a hypothesis. In other words, it's short of the word theory. Okay, that's a key thing to understand. The word theory is not a weak word. Scientists are trying to reclaim that, and scientists are actually very guilty of it being misused. I've probably said, well, that's just a theory. I've made that same statement myself numerous times, but I'm trying hard not to make it anymore because some anti-science people are making that a very big deal, and they're trying to exploit that. In some cases knowingly, but in other cases just not knowing any better. And the main thing is we really want you to understand science in general. So what we look at is we have an experiment or an observation that's made, and you get a certain result. And then you try to figure out some way to understand it better. Now, the initial assumptions might be I'm trying to understand what is the motion, or what's the shape of the motion, or what's the trajectory going to be shaped like. Hence, I told you balls will follow the path of a quarter of a circle or something like that, whose radius is blah, blah, blah. That doesn't necessarily tell you why anything does what it does, but it at least gets your foot in the door on knowing exactly the shape. And then later, if you figure out a physical reason for something to do what it's doing, then you might even be able to ultimately mathematically tie that back into the shape that you hypothesized. But the key thing is any motivation you have for making the hypothesis is fine. Galileo made hypotheses, and some of those were based on some really antiquated ideas. Kepler, who gets the advantage of having the scientific revolution somewhat named after him, he had really bad reasons for suggesting the model of the solar system was his particular model. Specifically, his particular model was that the universe was made up of a sun, and then it had 5 planets. At that time, they knew of Mercury, they knew of Venus, they knew of Earth, Mars, and Jupiter, and that was it. Earth is included, of course, and the moon is something as well, and the sun is something as well. But they sort of just treated all of those as what we call planetos. But his idea, which came to him one day while teaching a bunch of young kids, is, hey, the number of perfect solids in the universe is exactly the number that you would need if you wanted to take our solar system and put the sun at the center, and then put one perfect solid between it and Mercury, and another one between it and Venus, and another one between Venus and Earth, and another one between Earth and Mars, and another one between Mars and Jupiter. That would be exactly the number of planets that would be able to be fulfilled. And he just imagined that would not be coincidental. So he made up a whole theory of the universe this was Kepler, by the way, based on that idea. I think I might have said Copernicus earlier. I meant Kepler. But anyways, he made a whole hypothesis based on that. But because he was a good scientist, when he got a hold of Tycho Brahe's data, his model didn't work, and he just threw it away. And that's what you got to do. You can't even if you put decades or centuries of work into explaining a hypothesis or to creating a hypothesis, you still got to throw it away if it doesn't fit the data. It's just not going to work. So that's what he did. And the data came back as Copernicus's idea was not very good either. Copernicus had come in and said, hey, we've got too much complication in this. We seem to have lost our way from what Aristotle taught us, that the heavens are perfect, and therefore the perfect heavens must be immutable, meaning they can't change. So that means objects in the heavens can't speed up or slow down, because if they sped up, they would obviously be speeding up from perfection to a non-perfect speed, or they would be speeding from a non-perfect speed, which is unacceptable, to the perfect speed, which is acceptable. Again, this is very rudimentary logic, and they didn't necessarily understand all the big details, but that was the arguments that were made. So his argument, which is why I don't attribute his name, Copernicus, to the scientific revolution. I say there's a scientific revolution, and then there's a Copernican revolution. So Copernicus said, I can get just as good a results if I get rid of these epicycles and deference and equipoints and all this crazy stuff. It's something like 89 spheres on spheres on spheres that happen to occur when you make the geocentric model of the universe, according to Ptolemy and his people that followed him. You get 89 circles on circles on circles, and it's really a complicated mess. And what Copernicus was saying is we've lost our way. This is really a nasty mess, and it can be made much simpler just by going back to our roots, which is what Aristotle taught us. That's sort of the opposite of science. That's appeal to authority as opposed to appeal to evidence. He didn't really have any evidentiary reasons for going back to the heliocentric model as opposed to the geocentric, but he did it, and he did so. And when Kepler took the data that Brahe had created, he found that Copernicus's data from his model was really no better at predicting reality than the Ptolemaic model. It was slightly better, but it still didn't work. And the reason why was Copernicus said that the sun was the center, which was a good starting point. That's a heliocentric model. But he also said that, of course, all those crazy rules like the heavens are immutable and therefore can't change, those had to be there too. And since the heavens are perfect, only perfect shapes would be allowed. That means you're only allowed spheres or circles and stuff like that. So when you start doing that, you have to have circular orbits. Circular orbits are wrong. They're just dead wrong. Okay, they're very close, but they're dead wrong. So his data wasn't that good. So ultimately, Kepler threw out Copernicus's as well and made up his own. And Kepler came up with the idea that the planets orbit the sun in elliptical orbits with the sun at one focal point, that they sweep out equal areas in equal times, which force them to speed up and slow down, and that the square of the period is proportional to the cube of the semi-major axis. That was it. And with those laws, people could make predictions of where the planets will be hundreds of years in the future and hundreds of years in the past, and they get very accurate results. But it was all based on a bunch of crap. So don't feel bad what your motivation is to make a hypothesis as whatever way you make it, just do it. And if it works out, then maybe you'll later figure out why it seems to look like that. So what I'm showing here is you see some phenomena. A lot of times the initial phenomena is really just an observation. Sometimes, like in the case of special relativity, Einstein didn't really have any evidence to suggest that anything was wrong with physics. But what he did have was an understanding of electricity and magnetism and Maxwell's equations. And because of that knowledge, he knew that Maxwell's equations created waves, and he knew that the waves travel at the speed of light. And he got a bunch of paradoxes when he imagined riding on a wave of light. And the only way he could fix that paradox was by saying that the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. Upon doing that, then he got special relativity, which gave us time dilation and length contraction and E equals mc squared and all sorts of cool stuff. Okay, so it doesn't always start with observe either. It could start with hypothesis, or it could start with prediction. And the observed doesn't have to be an observation. It could have been an experiment, or it might have just been something you saw. But the main thing is there is some physical phenomena. A hypothesis, which is basically an educated guess, a guess based on what you've seen or what data you have, is made. And then from that hypothesis, you make a prediction. And if that prediction is correct, you've got to make it actually a falsifiable prediction. For instance, a non-falsifiable prediction is called a non-scientific prediction. All hypotheses must be falsifiable, or you're not doing science. It might be completely valid. It might be a really good reason for doing that, but it's not science. Okay. So you make these predictions, which have to be falsifiable, and then you make another observation or you do another experiment. And if your experiment confirms the prediction, then you pat yourself on the back and say, wow, you did really good. You've predicted one thing. Okay. And then you go back to your hypothesis, you make another prediction. You might have to tweak your hypothesis a little bit, maybe try to make some other understanding about something you saw in the other one, but you make a prediction and you observe again. And if you keep doing that over and over and over again for hundreds of thousands, or in the case of special relativity, literally hundreds of millions of times, then you slowly go from this hypothesis to what we would call a theory. So a theory is a very strong word for a sort of paradigm of thought that includes like a hypothesis, but it includes, real meat hanging from the bone, things that allow you to predict stuff, things that allow you to make very specific quantitative predictions that can very specifically and quantitatively be falsified or held true. And once you go through that cycle enough times and never, ever, ever once finding it to be an error, then you can move on to the level of a theory. So the special theory of relativity is a robust thing. It's probably the single most tested theory in the history of mankind. The theory of evolution is another one. oddly enough, Newton's law of gravity was another one, but we've since found some slight variations in its problems that luckily Einstein's general theory of relativity fixed as well. That's a theory as well. But notice how Newton's theory of gravity has a realm in which it's accurate, and you can still use it, and it's still called a theory because it's accurate in this case up to certain criteria, like as long as things aren't approaching the speed of light, as long as things aren't so massive that you have to use general relativity instead of special relativity, then there is a whole theory of Newtonian gravity that works. You can, for instance, get to Jupiter and back using a spaceship with just Newtonian's gravity. The problem is your clocks would be kind of jacked up, or even going to the moon, to be honest with you, would be enough to make your clocks jacked up, or even going to the International Space Station, your clocks are going to be off by using Newtonian gravity. But as long as you're not concerned about that and you're just wanting to predict where the spacecraft will be at such and such a date or something like that, then you can get accurate enough. So this is what I see the scientific process as. It's a cyclic process that never ends. And Einstein once said, no number of experiments can prove him right, and it only takes exactly one experiment to prove him wrong. And that's it. That's the strength of the scientific theory. It only takes one experiment well done, to prove someone wrong. Now, they might not believe you, right? But if someone else comes along and does the same experiment and gets the same result, and then some other people do it, then it's eventually going to tie back to say, okay, well, we have to throw away Einstein's general theory of relativity because we now have one experiment done by 6 different people, and they all got the same results, and they all said that Einstein was wrong. We'd have to say, as a bare minimum, Einstein's wrong in this case. Maybe there's something we're missing, but it might be that all of relativity is wrong. Okay. So that is the scientific process. Remember, the predictions have to be falsifiable to be scientific. And I can give you an example from my childhood. It was the first time I ever started thinking really about science so much. I went to Christian schools, private Christian schools, up until I think I was asked to leave my 9th grade year. I got in a lot of trouble. I was not a good student. I was sort of a loser. But anyways, I had this great opportunity to go to these really fine Christian schools, and they had great teachers that loved me like I was their own kid. And I had a lot of friends there, but I didn't like school at all. And I didn't like some of the things they taught me there as well, but it was more on the science side. It had nothing to do with religion. But one of the things that we toyed with in Christian school is, can God create a rock that's too heavy to lift? That's the kind of prediction that's not falsifiable, or it is falsifiable. It all depends. So, for instance, if you say, no, God can't do that, well, then that's something that God can't do. And if God's all powerful, then you've just contradicted yourself in saying that God's all powerful. If he could do it, then God's not all powerful, because there's some rocks that he couldn't lift. So it's just, that's a paradox, if you will. And if you have a paradox in something, that always points in the physical sciences, that always points to some misunderstanding of reality. Now, someone might come up and say, well, you don't understand God and the way things are done by gods, because they're higher species than us, and they can do things that we can't imagine. So us being unable to imagine a way that God could make a stone that he couldn't lift might just be a reminiscent of our inability to imagine all the things that a God could do. At that point, once you start to make that argument, then you're making a non-falsifiable hypothesis, because basically anything I give you, you can say, well, you don't see it the way God is, so you're not seeing all the different options. So another one, and this one is quite good. This is from Carl Sagan's book, Demon Haunted World. It's there's a dragon in my basement. I think that's the name of the chapter. And the scenario is boy tells Carl Sagan, "Hey, there's a dragon in my basement. Want to come see it?" And Carl Sagan says, "Oh yes, I love that. I've never seen a real dragon. I always thought they were mythical. This would be great. Can I see it?" He said, "Well, yeah, you could sort of, but he's invisible, right?" So it's basically you're making the claim that there's a dragon in your basement. And the first experiment that Carl Sagan offers is, "Hey, I'd like to see it." And he says, "Well, no, he's not that kind of creature. He's invisible." So that makes you think this might be a non-falsifiable hypothesis. Let's see how it goes. Yes, Eddie, you have a question?
So falsifiable, um, we do want our prediction to be falsifiable, or we don't?
Yeah, we definitely do for science.
We do.
Yeah,
So,
you have to have a test to make it false. You don't have to have a test to make it true, but you definitely have to have a test to make it false.
okay.
Weird, huh? But that's also sort of the strength of the idea of the scientific method and science in general, is because it takes hardly nothing to disprove, but it takes a lot to come anywhere close to something that people would call a workable theory. So yeah, in the case of the dragon in the basement, well then Carl Sagan says, well maybe he's not trying to make a falsifiable hypothesis. Maybe he's just telling me the truth. So Carl Sagan would then say, okay, well that's no big deal that he's not visible. I'll just pour some flour on the floor of your basement, and then I can see his little feet print walk across, and we'll see that he's there. He said, oh no, he floats. He's able to fly, so he hovers above the ground. There's another hypothesis that's been made that wasn't falsifiable, specifically because this person came with a workaround. Again, it might not be a non-falsifiable hypothesis, but it's starting to look that way. So he says, okay, well, no bother. I don't need to do it that way. How about I just get me a smoke machine that makes smoke, and then I can just watch as the dragon flies around in the basement. He'll leave a little path, like a cylinder, if you will, of his outline, sort of like Wile E. Coyote running through the end of a barn, and then it leaves the shape of his body in the barn wall. That was what would happen if a dragon flew through the smoke made from a smoke machine. And then the boy says, "Oh no, that won't work either because the dragon is immiscible. Like stuff just goes right through him like a ghost, so it doesn't even affect him. So he doesn't affect solid matter." Now we're getting into the realm that is almost certainly falsifiable, not unlike the ether that was originally hypothesized to fill the space around the planets, and especially between Earth and the Sun, for instance. So that kind of non-falsifiable hypothesis, though quite valid for a lot of things and quite useful for a lot of things, is just not useful at all in the paradigm of science. So science doesn't treat non-falsifiable hypotheses. Philosophy could, uh, comfort could. There's a lot of things from it that could work out fine. So I'm not trying to say that it's bad if it's non-falsifiable, but the point is, if it is non-falsifiable, that's not something you should be using science to discern. Okay. But as I said, once you do make these falsifiable hypotheses and they are every time correct, maybe you have a little bit here and there that has to be adjusted, but in general, you're essentially correct every time, and you never ever find a real mistake, then you've got a full-blown theory. For instance, there was a movie some time ago where someone made the argument that evolution was a non-falsifiable hypothesis, and that's a lot of people believe that, and this is one of those areas where it's perfectly fine to believe that if you want to. It's just you're just not doing science at that point. When they say it's non-falsifiable, then they're not quite being truthful with you. For instance, all it takes is one falsifiable hypothesis, and if you can meet that criteria, then you falsified it. So, for instance, very intelligent, I think it was Bertrand Russell said, well, I don't believe there's any cup and saucers flying around in outer space. Uh, that's, for instance, is a sort of non-falsifiable hypothesis. But in regards to theory, to evolution, someone said all you have to do to disprove evolution is show me a rabbit in the Precambrian. And that's a specific example, but there's literally an infinity of such examples. The Precambrian is when the first fossils showed up of life. Fossils of life showed up on the Earth, and that's a very specific layer in geology, and we can identify it by what's in that layer. And what we know is any layers that came after that would be post-Precambrian, and that's where all the life exists. And what we see is life getting more and more complex to higher and higher levels that we go in the strata of geology. And for instance, you do find, in different eras, for instance, in the Jurassic, which is broke down further and further again, you can find, for instance, velociraptors fossils, you can find T-Rex fossils, you can find all sorts of stuff. And in fact, if I remember correctly, I think the T-Rex and the Velociraptor are as far apart as Jurassic era is to modern day science. So some of it doesn't work quite the way the world has been explained in various movies, even movies trying to stay somewhat faithful to science. But the main thing is the way we see evolution is that evolution made more and more complex life. And we couldn't have gone through that more complex life and gotten that more complex life until we created less complex life. So we'd start off with, single-celled organisms and stuff like that. So those single-celled organisms that were able to make hard structures that could fossilize, they show up first in the Precambrian. If you find any living species having a fossil and it's at a lower, meaning below the ground and therefore older, below the level of Precambrian, and it's more complex than a single-celled organism, then yeah, that's a falsified hypothesis, and you'd have to completely rethink evolution. Because as it currently stands, evolution suggests that there's one common ancestor to everything on Earth, to every living thing on Earth. I'm not saying that we are related to all the other animals. It's deeper than that. I'm saying you are in some sense a cousin with a cucumber and with a blue-green algae and with maybe an octopus. Octopus is a little weird thing going on right now in science to some extent. I haven't seen the latest on it because that's not my field of expertise, but so I use that kind of hesitantly. But imagine that we're actually related to grass, we're related to trees, we're related to animals, we're related to every animal, in fact. And that's what the DNA and what the science of evolution tells us so far, is that we, the species of Homo erectus that became Homo sapiens, ultimately all descended from a common ancestor with everything else that's on the planet right now. Now, that also means that there are some other species that might not have been related to that common ancestor, but we haven't found those yet. But in principle, it could be some other species that aren't descendants. And I shouldn't say couldn't found it. I don't know that they found, but they probably have found other species that were the end of the line and therefore not related to us, except for some other common ancestor. So that's the current model of evolution, and that's also the way introduction to how science works. Does anybody have any questions on that how science works idea? So when you're reading section 1.1, oh good, got a question for me, Michael?
So just to clarify, anything that's falsifiable is anything that can be proven false, right?
Exactly.
Awesome. Cool.
Yep. If you can't prove it false or wrong, there's another word for it, then it's not worthwhile. That's why we still hold on to string theory. There's a lot of things we could do to show string theory to be wrong. There's not a lot of things we can do to show string theory to be right. I mean, there is, in the sense that string theory gives us back basically almost all of the science we already know. But the things that we want to predict with string theory that other theories don't give us are things that we're just not technologically able to prove or disprove right now. But the fact that we can disprove them, it means it's still a valid hypothesis. All right. So your book says in section 1.1 how science works. Section 1.2 is models, theories, and laws. It uses somewhat different wording for models, theories, and laws. He leans a little bit towards what I'm talking about, but he treats laws and theories a little differently than I do. Just remember, whenever you're taking these online tests and homeworks, stick to their answers. You'll be right. Okay. He doesn't talk the same way I do. I'm just trying to give you a better interpretation, I think. I shouldn't say better, I'll say more modernly appropriate, because I am a member of the skeptics sort of movement. So I follow what pseudoscientists have been doing in the past and specifically recently. And I'm trying to keep that aspect of reality on par. That's not something that physicists normally concern themselves with, because the physics as a science is not one that's that easily stolen by pseudoscience, whereas biology and stuff like that, and evolution and climate science, those are ones where it's a little bit easier for a pseudoscientist to jump in and steal stuff. I just happen to be a nerd that likes to, learn about everything. So I've taken some time to learn by watching listening to Skeptic's Guide to the Universe, reading all of James Randi's books, and reading Skeptic Magazine, that kind of stuff. So it's just Gene Coley's not addressing that problem. Some other authors have. For instance, one of the guys that writes Physics 100 level book, a conceptual physics book, he did take the time to cover that. And he did something more like the introduction to science that I do. So anyways, just pay attention to the book when it comes to questions about that. The next thing in chapter 1 is on measurement, uncertainty, and significant figures. We pretty much discussed that already in lab. I would tell you that there's a little bit more that we're going to do, and I told you we're going to cover error propagation. I would say the one thing that we're sort of missing from what we did in lab versus what your book does is your book does talk about the ultimate propagation of error formulas to some extent, and that's good. But he introduces something called a fractional error that I didn't introduce. But remember when I told you that 13.5 volts would be a measurement that you might get from a voltmeter? And you might call that 13 plus or minus 13.5 plus or minus 0.1 volt. I'll write this on my document here. So V equals 13.5 volts. If I read the manual for the actual voltmeter, then I might find that the V is 13.5 volts plus or minus 0.2 volts. This quantity right here is the uncertainty. And it's usually given the symbol sigma. And since it's the uncertainty in the variable V, we'll put V as a subscript. Okay. And then this quantity right here is the best estimate. Which we would normally call V bar, or we would call V like that, as I told you earlier. So there's something called a fractional error or fractional uncertainty. And it's given, if we're talking about specifically this variable V, it would be the uncertainty in V divided by V bar, or the uncertainty in V divided by V in brackets. Okay, so that's like literally the only thing that you're missing from here. They do something called quadrature, which we'll get into eventually, but you can't do anything with it the way the author introduces it to you. So there's no need in me showing you that. I just wanted you to know that fractional uncertainty is something. So in this case, what it would be 0.2 volts divided by 13.5 volts. Notice that has no units because the volts divided by volts gives you nothing. If I did divide the 13.5 by 0.2, I'd get 13.5 divided by 0.2, I'd get 67.5. Oh, I did it upside down. Sorry about that. I was like, how am I getting a large number? I get 0.0148, something like that. Now, sometimes we might actually want to convert it to a percent, and that's fine if you want to do that. But when you do that, you just have to put the percent symbol and then move the decimal 2 places to the left, or excuse me, to the right. But that's basically what it is. It's just that amount. And the reason why I bring it up is, in some sense, when you make a measurement, that's the important quantity. So if I take and measure something with a meter stick, and I know the meter stick has an uncertainty here plus or minus 0.02, then I take that 0.02 and I divide it by the actual measurement. That's the instrumental, or that's the fractional error for that instrument. And now I take that and use that in some other formulas. If I come up with an ultimate result and I round it to a place where the fractional uncertainty in that result is way smaller than the fractional uncertainty than I had in that one quantity, then I know I've done it wrong. Because if one part of a calculation needs a value whose uncertainty is, say, 0.1, and then you ultimately get a result whose uncertainty is 0.01 or 0.005 or 0.0007 or whatever, those are much smaller fractional uncertainties. You can't use mathematics to make your uncertainty smaller. The only way you can make your uncertainty smaller is use better instruments, i.e. ones with smaller percent error or smaller fractional uncertainties, or just improve the technology. Okay, so that's why I tell you that fractional uncertainty is sort of the one thing that can't get appreciably better than your measurements just by doing calculations with it. So I wanted to make sure I brought that in. Significant figures we already talked about. I did put the document up in Unit 1. So you'll see rules for sig figs actually written out in a document. So you don't have to just rely on the chat notes that I did last time. In section 1.4, we're talking about units, standards, and the SI system. So if you've ever been in school and encountered this thing, let's see how many of you know what this is. Has anybody ever seen this before? It gets worse too.
Is that like, is it like a unit of measurement then?
Yeah, I call it the G-man. And it's this god-awful mnemonic that we use to help us understand the crappy units that we use in what's called the imperial system, i.e. the system of Great Britain, that not only that we're the only ones that use, not even Great Britain uses it anymore. And what it's saying is that 1 gallon is equal to 4 quarts. That's why the 4 Q's are in there. And 1 quart is equal to 2 pints because there's 2 P's in there. And 1 pint is equal to 2 cups because there's 2 C's in there. And then you go further and put inside the C 8 little O's because there's 8 ounces in a cup. This is what you have to do if you want to convert, for instance, gallons to ounces. And it's god awful. It's a historical system of units. It's not a rational system of units. And that's what we have with the British system. And, because well, I'll just say for some reason, Americans have been very reluctant to switch onto a rational system of units. And we even do such horrible things in engineering as sort of cobble together various unit systems. So I don't know if you know this, but in like structural engineering, they use a quantity called the KIP. Have you ever heard of a KIP? A KIP? the kip is called this. 1 kip is equal to 1 kilopound. So yeah, that's how bad they've gotten. They're using SI prefixes for stupid imperial units, and it's just anathema. It's just a horrible thing. I don't know why they're doing it. They continue to do it, but either way, we're not using the imperial system. We're not using the British system. We're using the SI system, which you guys recognize as the metric system. Occasionally, of course, problems in real life come to us with measurements of units like miles, stuff like that, or inches or feet or pounds. And we have to know enough about them to convert back and forth. But right now, the main thing is you need to know the SI system. And the way the SI system is, and notice that's SI, it's the System International, which is the French version of international system, because it was started to be created when the French was the superpower on the earth, namely in the time of Napoleon. Napoleon was actually the first one to start setting this up. But it's a rational system of units where you have a base and then you have prefixes. And the prefixes are powers of 10 as opposed to historical things like 2, 4, 6, 16, 8, and stuff like that. So for instance, you have the base right here. And then if you want to be 10 times as big as the base, then you use something called the deca. So that's DA. If you want it 10 times smaller than the base, then you use deci, which I mistakenly put I was going to put an E on there, but it's just a lowercase d. If you wanted to go up by a power of 10, then instead of deca, anybody know the next one? This is, whoa, hecto. And if you want to go down by a power of 10, you do centi. If you go up by another power of 10, you go kilo. And if you want to go up down by another power of 10, you go milli. So this is milli, centi, and deci. And this is deca, hecto, and this one you're probably pretty familiar with is kilo. Okay, so you can have a base unit. The base unit might be a meter. The base unit, oddly enough, they don't call this the base unit, but it really is. The base unit for mass is the gram. So for here, you'd have like grams, meters, seconds, moles, Kelvin, all that sort of stuff. That's what your bases are. And then you can put this prefix in front of it. So you could, for instance, have a decigram, and that would be 1/10 of a gram. You could have a decagram, and that'd be 10 grams. You could have a milligram, and that'd be 1,000th of a gram. It turns out when we're using the SI system, the base really is the gram for mass. But when you go to use it in equations, when you use mass in an equation with the SI system, you have to use the kilogram. Okay. So when you're using various formulae, you have to use kilograms. So for instance, we're going to use the formula mass times gravitational acceleration. That will come out in the basic unit of the unit of force from the SI, which is the Newton. But it doesn't come out to be a Newton unless you use a kilogram in there. Okay. So that's the little caveat. I'll put this little, actually, I don't want to put that color because that makes it look kind of strange. Let me put a different color. I put that right there. There you go. Now, the way this continues to go is you then have 2 dots and you get a micro, 2 dots, you get a nano, 2 dots, you get a pico, and it actually goes on. So I'll just say dot, dot, dot. And then over here, 2 dots, you get a mega, and then 2 dots, you get a giga, and 2 dots, you get a tera. And then, of course, it goes on this way as well. So I've made up various mnemonics over the years, but I am chronically somewhere between 4th and 6th grade mentally. So all my jokes have to do with poop, pee, boobies, all the stupid stuff that young boys would do. So every time I make up a mnemonic, the P turns into prostitutes. So I would invite you guys to make up your own much better mnemonic, but I'll give you the start of mine. The great monarch King Henry died by drinking chocolate milk under numerous, and then I put in prostitutes because, again, I'm in a 3rd, 4th grade mindset. But that's a really nice thing, and having that system like that works really well, because if you don't want to actually do the hard math, it's actually a way that allows you to convert within the SI system from, say, gigahertz to microhertz if you wanted to, using this actual diagram. So let me show you what I mean. I'm going to steal this. I'm going to say copy. Now I'm going to say paste. So now I got all this stuff right here again. And I could continue with some other units down here, by the way. Hertz is another one. So let's say, for instance, we have 1, 0, 0, 0, 0, 0, 0, 0, 0, 0 gigahertz. And I would like to convert that to nanohertz. Okay. All I have to do is this. Now, it's important that you see what I'm counting here. I'm counting moves, not endpoints. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice I did count that, the base. 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 moves, not endpoints. Okay, so what that tells us is I need to take this I need to take the decimal on here on this gigahertz, which is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. The decimal's right there. I need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right there. So now I've got to put in all of these zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right there. And that would be nanohertz. Okay, so you can actually use this mnemonic as long as you keep those dots in there. Notice I had to go to each dot because each dot or each move is a power of 10. That's also why I had to include the base. But as long as you do that, notice it tells you not only how many places to move, but which direction. Now, was sort of not thinking when I chose to do gigahertz to nanohertz, and therefore I ended up making a really big, ugly number. I should have taken and done something like, let's say, 0.0000000000123, let's say megameters to picometers. Now you guys give that one a try. So in this case, we're going to go from megameters, which is right here, and we're going to go to picometers, which is right here. Notice we're again going from left to right, so we know that. And I then just got to count everything. 1, 2, 3, 4, 5, 6. Ah, dang it. 1, 2, 3, 4, 5, 6. Dang it. It keeps doing that because there's stupid things on auto or whatever. And actually, I can't get it out of there. So 1, 2, 3. Ah, dang it. Every time I pause, it does it. So this looks like it should go 18 places again. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That was 12, 13, 14, 15, 16, 17, 18. And that looks like what I'm supposed to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So yes, 18. So I'm going to say equals 1, 2, 3, which would be right here. So I'm going to go 2 places past that. That's 12 at the end of there. So 12, 13, 14, 15, 16, 17, 18 picometers. So that's another way you can actually do it. Notice it also goes the other way. Like if you have something on the right hand side, you can go from pico to kilo, but then you're moving the decimal to the left and all that stuff. So that's something you got to be able to do. I do not recommend you doing this. I recommend you doing this just as long as it takes you to get used to knowing these prefixes. I suspect you should know. In other words, I expect, not suspect. I expect you to know Tera through Pico, and just about everybody's going to expect you to know Giga through Nano. So let me just write those out again one time. This is Tera. This is Giga, which you might know from Back to the Future, and this is Mega. This is Micro, Nano, and Pico. Okay. So this mnemonic can help you in a crunch. It can quickly allow you to do this stuff, but really most people that do this is a lot of times it's in the more biological sciences where they just need to make some conversions and they really don't need to learn a lot of math necessarily. However, biology is getting more mathematical by the minute. I've been studying a little bit of neuroscience lately, and they're doing computer programming and all sorts of stuff in there as well. So the biological sciences are getting more mathematical, but the main thing to know is You can use this to get from one prefix to the other, or from a prefix to a base, or from a base to a prefix. And you can also then use it to recognize what the powers are. So for instance, you know that, let's try it this way. If I multiplied the base by 10, I would get deca. So dA equals 10 to the 1. Hecto is equal to 10 to the 2. Kilo is equal to 10 to the 3rd. And then that dot doesn't mean anything. That second dot doesn't mean anything. But the mega means 10 to the 6th. And the giga means 10 to the 9. And the tera means 10 to the 12th. And I might have hemmed and hawed a little bit on trying to decide whether to write TERA or TERRA. That's because I couldn't remember which the spelling is. The front cover of your book does tell it, as also there's an appendix. But you can also go the other way, and you'd see that deci is 10 to the negative 1, which is equal to 1 over 10. Centi is 10 to the negative 2, which is equal to 1 over 100. Milli is equal to 10 to the negative 3, of course, which is 1 over 1,000. And then we get to micro, which is a Greek letter mu. It's 10 to the negative 6. Nano is 10 to the negative 9. And pico is 10 to the negative 12. In fact, the next one's femto, which is 10 to the negative 15th. But that's what they do from there on out, is they go 10 to the factor of 1,000 from one to the next. And what I mean by writing this is, if someone says that you have 1 gigahertz, that means you can literally replace the giga with times 10 to the 9, like that. And that is your actual number. So you're literally just replacing the prefix with that power of 10. Does that make sense? So that's how you can learn what each of those powers of 10s are, because if you memorize or make up a mnemonic to come up with the T through P, you'll have it laid out, and then you can just go through and count the powers of 10 by either a dot, a letter, or an underline for the base. And the base is obviously 10 to the 0 power, because everything raised to the 0 power is 1, except for 0, in which case it's 0. So that fixes all that, lets you nail it down. But that's not really the way we use it to convert units. The main thing is we need to know what those prefixes are, and then how to convert units. So that's what I'm going to go into now. Well, before I go into that, let me talk a little bit about what your book does. So your book then says, now that I've given you this idea, or actually even before they give you this idea, they first talk about the base units. And fundamentally, the base units really are the units of length, time, and mass. So another word for the SI, another word for that, of course, we call it the metric system. But another word for it is the MK, and that's actually supposed to be a lowercase k, in the MKS system, which means meters, kilograms, and seconds. And I only capitalized the M because it's the first letter. I didn't have to. You could have called it lower M, and then KS. I've seen people write it capital M, capital K, capital S, all that stuff. The main thing is when they say the MKS system, they're talking about the SI system. And the base units are the meter, again, the kilogram with the caveat that I gave you, and the second. So you need to know that we have to have some standard with regards to what an actual meter is, what an actual kilogram is, and what an actual second is. So we initially had neat things like the meter was 1/86,400th of the distance between some place on Earth and some place on Earth, all sorts of crazy stuff like that. However, we have discovered that over time, things like that on the surface of the earth change, even those big quantities. For instance, we had an earthquake a few years ago, and Mount Everest changed its peak height by on the order of a whole meter. So we can't even use that stuff. So we've been trying to find more concrete ways of determining things. What we had for a long time was for the unit of mass, we just had a sample of mass. And we would keep it in a very controlled environment where the temperature and humidity didn't change much. We put it under a glass container at, right at 1 atmosphere, and then that glass container was under another glass container, and that glass container was under another glass container. All of that just to protect that pristine little unit mass from getting jacked up. So we can use that for a long time. We had the same thing for the length of a meter. It was a platinum iridium rod that had 2 etch marks on it, and those etch marks were what we've historically called the unit of the meter. And that was fine too. And then the second was left as, that's where the number came from, 1/86,400th of a day. But again, the day changes. If you might not know this, but what we've discovered is that the moon pulls on the earth and causes it to slow down its rotation rate, and the earth pulls back on the moon and causes it to change its revolution rate. And because of that, we slip in little basically little units of time, sort of like leap year, where we put in leap seconds, just because of that. So even the day being 24 hours isn't necessarily a good standard because it changes from time to time. So what we're currently doing is we've ultimately defined the unit of time to be very specific. So the time turns out to be originally, like I said, 1/86,400th of a second. But now what we treat time as is the 1 second is the amount of time required for a certain number of nuclear reactions to occur in cesium-137. So 1.000 with a bar over it, that means exactly 1 second, is defined to be the time required for 9,192,631,770 periods of radiation. So we set up a Geiger counter basically with cesium-137, and it has a nuclear decay that occurs every 1/9,192,631,770th of a second. And we wait for exactly that many of those transitions to occur. And the instant that 770th one occurs, boom, we say 1 second has passed. So that's a very, very specific thing. And it's off by, 1 in like 10 to the 12th decimal places every century. So it's really a really high degree. So that's now the unit of time that we use. And now that we have that precise of a unit of time, we can say that length, the meter, that's now defined in terms of the distance light can travel. So 1.000 with a bar over it meter is defined to be the distance light can travel in a vacuum in 1/299,792,458 of a second. So the unit of length now, 1 meter, is defined to be the distance light travels in 101 over 299,792,458 seconds. That means C is exactly 299, C being the speed of light, 299,792,450. Whoa, wrote the wrong number again. 458 meters per second. And this literally has a 0 with an infinite number of decimal places. Okay. Yeah, Megan, go ahead.
Oh, I just wanted to know what does it have to do? Why is vacuum important there? Like,
Gotcha.
what
So-
if it's not there?
Yeah, it turns out that that light does actually slow down when it goes from a vacuum to air. It doesn't slow down much in going to air. In fact, it changes by, if I remember correctly, 0.0006 seconds are basically 0.006. If you multiply 0.006 times the speed of light, that's how much it changes by in going from vacuum to air. If it goes to glass, it changes by a factor of like 1.33. If you go into water, it changes by a factor of 1.5. It always slows down in other materials. So they had to specify in a vacuum just so they get the most accurate speed.
You said 0.006, right?
Yeah, if I remember correctly, I'm just pulling that out of my memory, but yeah, that's
Alright.
roughly what it is.
Thank you.
So we are still left with the unit of mass, and what we're currently using is a 1 kilogram object. So for mass, we actually have a physical object, and it's a platinum iridium cylinder. And it's kept, like I was telling you earlier, under a glass, under another glass, under another glass, that sort of thing. And it has a height h and a radius r, but since it has a density that's equal to a constant for platinum iridium, that's density in kilograms per cubic meter, and a volume that's equal to a constant, which is pi r squared h. Okay, so in order to make this the ideal physical object, what they needed to do was minimize the surface area. And this is your first chance to solve an extra credit problem. The extra credit problem is this. I want you to find a relationship between R and H. Or a formula, if you will. That makes the surface area which I'll call S, minimum. Can anybody guess what the formula for the surface area of that cylinder is? How about the surface area of the top?
I think it's pi
Mhm.
times radius squared times height,
That's the volume.
the surface. Okay.
Yeah, you got that one right for the volume. But what about the surface area? So you've got a circle for the top, a circle for the bottom, And I think y'all can probably figure out what the surface around the edges is. What kind of shape is that? If you took like a beer can and you cut vertically right along the side of the beer can from the top to the bottom, and then you cut right around the edge where the top and side meets, and then right along the edge where the bottom and the side meets, and you laid the label part out, what shape would that make? Let me check my chats in case somebody's putting something there. Yes, you're right, Joy and Rain and Jude. Yes, it would make a rectangle. Okay. So it turns out that the surface area is pi r squared for the top plus pi r squared for the bottom. So that's 2 pi r squared. And then the rectangle is basically r times h. Or excuse me, 2 pi r for the length. And then the height is h. So that's the formula for the surface area, 2 pi r squared plus 2 pi rh. Now, in order to do this, here's the big hint, okay? What you're supposed to do is find a minimum. Does anybody recall from your calculus class what you're going to do to calculate a minimum?
Find your critical values.
Derivative?
Exactly, find the critical values, and as you guys said, derivative. So what are you going to do with the derivative? You're going to set it equal to something, right?
0.
Yes, so you take the derivative of the surface area and set it equal to 0. Now, here's the problem. As the surface area is written right now, it has two unknowns. This is what we call multivariable calculus. You don't do that. That's not required for this course. But because I told you the volume and the density are constants, you can use the fact that the volume is constant to get a relationship between H and R, or between V and R, or something like that. So you can eliminate one of the variables, either the R or the H. Sorry, I should have used the same R in both cases. You can eliminate one of the variables by solving the V formula. V is a constant, so you don't have to worry about that becoming a variable. So you solve for V, you solve in V for either R or H, and then replace R or H in the surface area formula. Then you'll have a surface area formula that has only one unknown, either R or H, right? The V is a constant, so you don't have to worry about that. So then you take the derivative of that, set it equal to 0, and solve for R or H, whichever one you have. And then once you get that, you plug back in the relationship between volume R and H so that you can get just R in terms of H or just H in terms of R. The second step, does anybody recall how you make sure it's a minima as opposed to a maxima?
Do the second derivative test.
Exactly. You take the second derivative, and if the second derivative is positive, then you know it's a minima. If the second derivative is negative, you know it's a maxima. And if the second derivative is 0, you know it's a point of inflection. So that's your extra credit. And it's already posted in Unit 1, including a description of it and a place to turn it in. So that's enough for right now. Class is just supposed to end. We actually started a little late, so I hope you didn't mind me going over by 3 minutes. I would have liked to cover more, like I need to cover how units are converted and also dimensional analysis, which I haven't done yet. But we'll finish that up next time. It's not a problem. You've got plenty of videos to catch up on it too. I've put a bunch of optional videos in Unit 1 that you can watch. They're all links. Most of them are just to my YouTube channel, so you can do that. And there's also some links to my Google Docs, so you can get the notes from previous YouTube videos. But we're done for the day. If anybody has any questions, I'll wait around for the last person to leave before I leave. But I will see you guys again at noon on Wednesday via the same Zoom setup here. And I'm glad you made it, Megan. I was looking for your email and didn't get it. I was worried.
Professor, do you know when this video will be posted?
It should be sometime tonight. It takes a few hours for me to convert and then upload. because I live out in the Booneyville of North Carolina and we don't have that good of internet. But I usually get it by the same day, if not the next day.
Okay. All right, thank you.
No problem. See you.
Professor, just to clarify, so Megan is here in the classroom with me. I'm Guinevere. I think I already sent you an email, but I haven't sent you an email for the class. I'm gonna send that after this class is done, and you should be receiving one from Guinevere Simmons.
Guinevere?
Yep.
Okay, no problem. I'm glad you told me that because I wouldn't have counted her as present otherwise.
Thank you. All right. Have a
welcome.
good day.
You have a good one.
Thank you.
Thank you. Appreciate you all coming. Again, I apologize for making it this online stuff, but we'll get over it. You guys will rock it.
I have a question regarding like homework stuff.
Okay, go for it, Michael.
Yeah, so just in terms of what stuff is due, of course we have like the extra credit and things like that, but what does it look like for what we need to do actionable wise past this class?
Okay, so and this will be spelled out a little bit on the syllabus when you get that. But mainly every week you're going to have a chapter homework or up to 3 chapter homeworks usually, maybe some extra credits and a lab. You need to do those specifically because without solving the problems, you really are not going to be able to succeed on the test. And then when test time comes around, I try to do at least an online test every 2 chapters just to make it a little easier on people. Then what you would do ideally is take the practice test as many times as you can. And that will almost certainly assure you somewhere very close to 100 for the actual test, because I usually use the exact same questions that appear on those practice tests, even though every time you take it, you get a different set of questions. You're not required to take the practice test, but you'd be kind of crazy not to. And I give you practice tests for the face-to-face tests too, and these are often comprehensive and a lot bigger. But the more of those practice tests you've done, the better off your score will be. And at the end of the semester, it just sort of all works out. I get a lot of A's. I get several A's. I get a lot of B's, a good number of C's, and then D's are quite a bit less than the B's or A's, and F's are usually 1 or 2 total out of the semester, if any.
Okay, thank you so much. Have a good
best
one.
thing you can do is just solve as many physics problems as you can find. Anybody else?
I got a question.
Yeah, go for it, dude.
So on Canvas, I see like 2 courses for physics. Is one for the lab and one for lecture?
We're only going to use the lecture one. The lab one I had to make visible in case I had anybody enrolled in my lab, but not my lecture. So I made it visible long enough to send the email, and now I can erase it. So it's not going to exist anymore, probably tomorrow.
Oh, okay.
Yeah, I
All
try
right,
to
thank
do
you.
everything right through the one port, so you don't have to go to multiple places. That's also why I synced our MyLab and mastering, so you can just go through to mastering straight from Canvas, and you shouldn't go to mastering any other way.
That makes sense. Okay, thank you.
You're welcome. How about you, Van? You go by Van or
Yes.
Thaman?
Yes, it's Van.
Okay.
Okay. So I have a question about the textbook. Like because my friends have this kind of physics textbook and he passed it to me.
Right.
So I don't kind of like, do I have to purchase the online textbook just for doing the homework and assignment that you grade in the campus?
You at least have, well, you at least have to have access to the 5th edition homework setup. And last I heard, MyLab and Mastering or Pearson was not selling that separate from the ebook. If they are, then you can do that. Because to be honest with you, one book's as good as another. in most cases. Like there's a book by Giancoli, there's a book by Surway, who was a professor at JMU. That one's quite good. There was a book by Tanner that was at Georgia Tech. That's a good one. There's a book by Halliday, Resnick, and Walker. That's a good one. All those books are pretty much equally good, long as they have physics for scientists and engineers with modern physics. They'll all be equally good. But in order for you to do the homeworks, you have to have access to that website. And if I ever make up an assignment, you're either going to have to, from the textbook, you're either going to have to borrow someone else's textbook long enough to get that particular assignment out of it, or you're going to have the book. So you don't have to buy another one, but you at least have to have access to the 5th edition through the portal at MyLab and Mastering.
Oh, okay, got it.
Okay.
Yeah, I just like wonder if I like could separate these two and just buy the access to your homework, not the textbook,
If they'll let
because
you
it will
just
be
buy the
cheaper.
access, that'll be fine. I'm not gonna, I
Yeah.
wouldn't fight you on that. And they're still getting their money. I mean, Pearson's paid me a lot of money over the years I write these websites for them. So as long as you're getting the website access, then you're definitely paying them, and it's all fair. You're not ripping anybody off. Everything's good.
Oh, okay.
Okay.
Thank you. Yeah, I think that's all.
Okay.
Have a nice day.
You too, Van. Take care.
Thank you.